Hello students, in this session we are going to study the limit of eccentricity for circular section. This is also called middle 1/4 rule. We have already studied about the limit of eccentricity for rectangular section. Now we are going to study the circular section. To a column there is a short column, this is a short column, this is not a long column. Short column or any compressive member like concrete, and we are applying a load P in compressive manner at some eccentricity, suppose E eccentricity, and you already know that there will be direct stresses, like this. It can be converted to two loadings, direct stresses and bending moment, which has the value of PE, load multiplied by the perpendicular distance PE. So it can be converted into two loadings, direct loading and the bending loading, right? Direct loading has direct stress, bending loading has bending stresses. Bending stresses are tensile as well as compressive. On one side it is tensile and one side it is compressive. On this side it is compressive bending stresses. This we have already studied. On this side there is tensile bending stresses. And the total stress, the resultant stress will be the combination of direct stress and the bending stress. And when it is combined, that our member will not fail in compression, it will fail in tension. If there is tensile stresses in the material, there is failure chances of this material, right? So what can we do? We can do that the eccentricity should be under a certain limit. If it is under a certain limit, that's why the name is limit of eccentricity. If it is under a certain limit, then there will be only compressive stresses and there will be no tensile stress developed in the material, and the material will be safe. So let us suppose we have applied a load P, and this P is this P. Seeing from the top, it is at a distance of this. And we want the limit of eccentricity, that there should not be any tensile stress. And if there should not be any tensile stress, in that case the direct stress should be either equal to bending stresses, maximum bending stresses, or greater than bending stresses, right? So for safe loading with no tensile stress, sigma D should be either greater than or equal to sigma B maximum. And what is sigma D? That is load upon area. And what is sigma B? That is M is PE Y upon I. And from here we can find out E should be less than equal to I by Y upon area. So that should be less than equal to Z upon area, section modulus upon area, right? This we have seen in a rectangular section also. But what is the section modulus over a circular section? If it is a circular section, what is the section modulus of a circular section? That is pi by 32 d cube. And what is area? Pi by 4 d square. So eccentricity should be less than equal to, put the value of Z. Z for circular section is pi by 32 d cube. Go to the section of section modulus, and area is pi by 4 d square. Put these values. So this is pi by 32 d cube upon pi by 4 d square. So this implies E should be less than equal to, that is d by 8. So eccentricity should be less than or equal to d by 8. It means this value should not be greater than d by 8. This value should not be greater than d by 8. And if we see on the other side, if the load is applied on this side, then also we will get the same thing, that the load should not be, the eccentricity should not be greater than d by 8, and this d by 8 plus d by 8, it will become d by 4. So diameter by 4. Similarly, if the load is applied here, the eccentricity should not be greater than d by 8, and same way, if the load is applied here, the eccentricity should not be more than d by 8. So from all sides, this part gives the kern in which our material is safe, right? So basically we are getting a kern, an area in which we are safe and there is no tensile load is there. This and this, d by 8 from the center, d by 8 from center on all sides. So this area is a safer zone where there is only compressive stresses are there and there is no tensile stress developed in the material, and this area has a diagonal width of d by 8, d by 8 plus d by 8, this is d by 4. So this is d by 4 on this side, and also also right here, this is not a rectangle, this will become a circle also. You will get a circle because this is d by 8 in the circular section, right? So you will get this type of kern, circular kern here, right? So here it is not rectangular basically, by mistake I have done this. This is basically circular zone because it has an diameter of d by 4, right? So this is a small circle inside like this, in which, because it has a diameter, right? So this is the kern, this is that kern, right, which has a diameter of d by 4. Similarly here, on this side also, you are getting this kern of d by 4. And in this part of the material is safe, and this is the kern, the safe part of eccentricity, where if we apply the loading there is no compressive stress, right? So this is the kern, 1/4 of the dia. That's why it is called middle 1/4 rule, right? So kern in circular section is 1/4 in diameter. Kern for circular section is 1/4 of diameter at center, where there is no tensile stress developed if load is applied eccentrical, right? If load is applied eccentrical in this area, there will be no stress developed anywhere in the material, right? So this is the limit of eccentricity for circular section, which is also called middle 1/4 rule.